So, good morning again, everybody. Today we are going to improve our program on Rayleigh fading channel simulation. We started last time. We are going to add some noise and variable strength of signal to noise ratio, and accordingly display plots of symbol error probability and bit error probability. So that's what we are going to do today for three cases. Direct line of sight signals, so no fading, Rayleigh fading channel, and Rayleigh fading channel. So we are going to start with opening our program we had completed last time. And I'm going to show you first, before we go further, some tweaks and improvements to this program so that you can also actually implement them in your third practical exercise part. Yes, so you can make a single report for this third and fourth practical exercise, of course, because it uses the same, no, at least partially the same code. But, well, if you'd like, you can also make a separate report. It's whatever mode is more convenient for you. So let me run this code first, remind you what we had obtained. So we have obtained 3 plots last time, and here we had constellation diagrams for Rayleigh and Rayleigh fading simulations. Yes, here we had so impulse response of real part and imaginary part, and accordingly amplitude response or amplitude frequency response for the imaginary and the real part for here we had Rayleigh channel. Yes, and here we had Rayleigh channel. So I find out some workaround to make a caption of the entire plot window. So I'm going to demonstrate you now how we can make that. But before that, also let us slightly improve the performance of our program by telling, so here we have 10,000 data symbols, and actually there is no need to plot all the 10,000 symbols in the single plot. Well, I have just closed it, which was, let us make it again, the first figure, yes. So it will be totally fine if we took only 1,000 of these points and displayed them, and it would also improve the performance of the program. It will not make so long thinking time, let us say so, and this will be useful for us later on when we will increase the number of points to 1 million. Yes, so if we having some issues already drawing at 10,000 points, then drawing 1 million points, which will be completely unnecessary, yes, will also be much slower. So in order to avoid that at this early stage, we are going to make some small modifications. So we are going to plot each 10th point instead of every point. So for that, we need some downsampling factor n down, yes, which can be calculated as n divided by 1,000. So that would be step for plotting CAM16 signals. Here, accordingly, when we plot them, ideal signals of CAM constellation here for Rayleigh channel and for Rayleigh channel later on here, we are going to need some index, yes, starting, index starting from 1 with a step of n down and ending with n. And here we accordingly add this index, idx. I'm going to copy it, real part and imaginary part. And here, wait a minute. So CAM map is only single value, so no need to use the indexes there, only here with the Rayleigh channel, like this, right? So let us try and run this script now and see if it draws plots faster, and if these plots miss some information, some important information. Well, they do look much more scattered, So we might actually change this to step somewhat smaller, like maybe 100. So the step of, well, we need smaller step, then we divide with, for example, 5,000. And for the 2,000, well, looks like more 3,000 then to get good enough plots and at the same time high performance. Yes, so I would divide by 3,000. Again, it may be not so much benefit for us now, as we have here only power of 4. But let me try and make it million now, and let's see how fast it goes this way, and how fast it will work if I specify here 1. Yes, so basically n down will be 1. Effectively, it's gone. Yes, and then if I try to plot, it takes some time for computer to actually generate these plots, right? So in order to avoid that problem later, yes, we are going to disable this. And here you also can see that it's not really necessary to draw this much points. Also, I don't know why it's drawing these plots so slowly. Probably because it was preoccupied. Also, if I try to maximize this window, it will also lag. Yes, so you can clearly see what is the problem and why I offer you to make this maybe smaller. Also, we don't really see any more of this pattern we were able to see in dry sand channel before, right? So again, I would recommend to downsample the displayed data. So we do calculate all of the data, but we only show part of this data sufficient to actually observe the modulation results. Yes. So that is first improvement to the program. So I'm going to return power of 4 here, as it was for the task 3 before. And then let us make this how to say it, general title for the entire window. So for example, in the first window, we had CAM16 constellation diagrams for two different channels. So what I'm going to do now is to add some text here stating that I'm having the plot of CAM16 constellation diagrams. So unfortunately, if I was to use simply title, it would draw the title for one of the plots instead. So I need to use some workaround, which looks like follow. So here, when I have drawn the last plot, yes, I'm enabling additional plot drawing. So basically, I say that I'm going to hold it on. And here, accordingly, I'm going to hold it off. Yes. And in between these lines, right at the end, I'm going to use a command called axis. Yes, so I'm going to specify some parameters of the axis to actually make this title. Yes, so how I'm going to do that? First of all, I'm going to add this command title here and accordingly specify the new title. Those will be CAM16 constellation diagrams. Yes. And if I run this code, we will only see, well, if you look closely, you will see that below this axis, I have my old plot. So what I need to do now is to hide this axis and display only this title. So I'm going to do that by specifying additional parameter called visible and set it to off. Right? So let's see how it works. And now we have this merge title, right? So similarly, we are going to add it to 2 more plots here and there. But again, I'm sorry for a little interruption. I need to check what my dog did. I'll be back in a minute. So yes, sorry again. He's too small to go outside yet, so we have to take care of everything right in flat. So now everything is fine. We can work. So as I said, we're now going to do the same thing for all the remaining figure plots. So accordingly, hold on, hold off. And basically, well, okay, I'm going to copy this entire thing. So here I put hold on. Then I copy this, the new title, which is so impulse response and AFR for Rayleigh channel model. Again, I'm going to copy this, put it here, and set hold on here. And accordingly, this will be for Rayleigh channel model. We might actually make a text string and specify some parameters even, yes. So for example, for Rayleigh channel, I'm going to do it like this. So this will be string message like this. Oh, read this, and I'm going to so k is equal to concatenated, right, with num to string k, right? So because we sometimes specify this k parameter as 2 and sometimes as 5. Yes, so I'm going to add this number in the title itself. So now what is going to happen, real value k is going to be converted into the string and attached at the end of this text string. And here I'm going to specify this string message. Anyway, so let's see if it works. Yes, it works. Now we can see k parameter value inside here as well. So with these improvements, we are going to put stop to the practical exercise 3 and make this file as a copy for practical exercise 4. So we are going to save this file as practical exercise 4 code. So I already tested this practical exercise, so everything working fine, and we will make it today. And now we are going to make some additions to this plot, to this practical exercise by accordingly specifying maybe a new section of this file. Yes, so here I'm going to mention that here we have practical exercise 4, simple error rate and bit error rate simulation. That is our task for today. And accordingly, we are going now start it. So as you can see, the parameters will be the same. So I don't have yet tasks and report contents file prepared because I have just recently finished this. working on this practical exercise, and I believed it was much more important to actually make sure that everything works as intended, then I will eventually this week make the same code, so it's the same text with instructions what you need to put in the report for all the practical exercises we had so far. So for this one and for 2 previous as well. So this impulse response is just exactly the same as it was in the last practical exercise. Yes. So from this point of view, no new parameters are specified here. But well, we will have to add some more advanced parameters as we go. So we'll start with plotting BER and symbol error rate probability. Yes, because it doesn't require us to change in any way this ideal signal, right, generation. So this S loss signal is actually perfect signal. Yes, if we plot it, yes, it will be accordingly these red crosses we had. Actually, we found our constellation map from this ideal signal. When we will switch to bit error rate calculations, then we will need to change the way we generate the signal. So we will modify this code later, but right now we don't need to do anything of that. So, so yes, we can start working on our new code section here. So let us first check how it works without noise. Yes, so what we need to do is to add detector for our signal. Yes, so we need to make demodulate signals. And for that, in order to, how to say them, see these 2 signals as different signals, because recently we have named them just SRX, and here we have them overwritten. So for that reason, I'm going to say that this signal is going to be Rayleigh signal, here accordingly as well. And this signal is going to be Rayleigh signal, and here as well. Now the idea is quite simple. We will make one detector, for example, for Rayleigh channel or for perfect signal, and then accordingly we will duplicate it and replace some input signal. So in fact, we already had these tasks somewhat shown during our second practical exercise. So for example, sim no filter. As you can see, here we have this demodulation procedure. And in fact, I have uploaded some additional material explaining how to work with that. So in this particular case, we are talking about this bachelor level course practical exercise. Yes, so you don't need to do this. You don't need to do this. I just added it because it has some useful information in it. We will get to this simulation, symbol data and binary data generation later, to this constellation also later. But what is now most important is how this detecting and error counting will be implemented. So in order to, I'll say it, in order to make this detection, we are going to make replicated matrices of our data. So here you can see some noisy signal values, because originally our signal should be like +3 -3i, for example, -3 -3i. Sorry, it is also minus here, not plus. So here we have it as a minus. Next signal is -1 +3i, and so forth. And they have been somewhat degrade because of the noise. Yes. So basically, we can say that our noisy signal is this column. So what we are going to do is to replicate this column 16 times, right? Because we have 16 possible symbols, starting with -3 -3i and going up to +3 +3i, right? So in total, 16 different symbols, combinations of +-1 +-3. So we have 16 columns of that, and we also have this constellation of all the possible symbols as a row vector, yes, which we replicate n times, as many symbols as we have. So basically now we have two n by 16 matrices. First matrix contains values of the received signal. Second matrix contains values of the perfect signals. Yes, and accordingly we are going to find the difference between received and the how to say it, perfect signal values. Yes, this distance is actually metric for detector to make decision on, and each column will have the distances between received signal, this signal, and each of the possible perfect signal points. Yes, and accordingly the reception is made based on the minimum of this distance. So we calculate minimal distance, we find not only this distance but the symbol itself, right, which is positioned in the constellation, and accordingly then once we have it we can calculate number of errors. So here we calculated binary errors, we'll get to that later, but right now let us see and copy this part of the code and start working on it. Right, so basically we are going to reuse some code from the second practical exercise. So I need to unident it. So I'm doing it format unident section, right? This command is demodulate line of sight loss signal. So no fading in this signal. We should get 0 errors. So that's why we start with this signal, just to see that everything works properly, so we can use the same approach for 2 remaining signals, which unfortunately, even without noise, will produce quite a lot of errors. So, yes, as I said, here we are going to replicate the signal, but please keep in mind that we are actually going to, how to say it, add noise to our signal eventually. So for that reason, I'm going to make this SRX signal, which right now is going to be as loss signal. Yes, so ideal CAM16 constellation signal. Oh, wait a minute, rather than ideal, in fact, we do have, yes, we should use this ideal. That is correct, yes, because otherwise we already have some fading effects here applied, and well, this is not exactly what we want to do. So we are going to use this ideal as loss signal. So, and later, actually let us make it now. Noise signal, yes, so we add noise to our ideal signal. So received signal as signal plus noise. And we are going to specify noise right now as 0. Yes, so basically we don't have noise right now, but we leave the space for this option to be included today a little bit later. Yes, so this is going to be noise signal. And it's okay to add a single number to the entire vector. In Octave it will work like this. And the only thing we need to know now is this signal a row or a column before we start replicating it. So here we have replicated this signal by a column. So we expect this signal to be a column. So let us check if it is a column. Let's display first 20 values, and we see that it is actually a row. So we need to transpose it here, SRX. And for complex numbers, we actually must be sure that we use this dot transpose, because otherwise, if I use simple transpose like this, it will be a column, But you will notice that imaginary part has actually been conjugated, right? So we had originally we had -1, -1. Here we have +1. So the sign has changed. In order to avoid this effect, we must transpose correctly for the complex number element by element, like this. So then, as you can see, the sign didn't change. So that's quite important. So for complex number, there is a difference between this transpose, which returns the conjugated result, and this transpose, which returns the original results, right? So we are going to perform this transpose right in this repmat operation, which simply copies our column 16 times and generates received data matrix. Now we need to repeat the same procedure for our constellation diagram map, yes, which again might be a row or the column. So let's see what it is actually. So this is going to become 16 map, a row. So it's okay, we need it as a row, and accordingly can replicate, can replicate it as it is, right, without this additional transpose. So I'm going to erase. So what this command does, it makes sure that any array is converted into vector, and more specifically into column vector. So for any of these arrays, after using it, you are going to get a column vector, even if it was originally a matrix. For example, let's show like this. So A is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. A matrix, yes. So if I use this operation, it's being unwrapped into a single vector, and more specifically column vector. So in this case, whatever it is, row or the column, we can always make sure that it is a column. And in fact, it's quite a good idea to do so too, because we no longer depend on this. So I'm going to actually add it here as well. So regardless of is it a vector row or vector column, we always will get it as the column, in fact, right? So no longer need to use this transpose also. Yes, so if I use it like this, it's going to be a column, right? So, okay, that would be prepare matrices. So that would be matrix A, signal matrix, matrix B, constellation matrix. So replicated a Rig signal matrix, replicated CAM16 constellation matrix. Here we are going to add noise to signal. And this is our general command title, what we are currently doing in this section of code. Right. So let us go further. Now we can calculate this distance, this distance. So yes, index like this, and demodulated signal like this, right? So basically, well, actually, we don't need this line because we already have it as a vector. If you recall, here in the second practical exercise, I think we have been generating our CAM16 matrix as a matrix. So let me double check it. CAM16 simulation. Yes, it is a matrix. Yes, you can clearly see CAM16 map, one row, second row, third row, and so forth. So we needed to convert it into the column. This time, we are going to specify this constellation manually as a single row. So, and in fact, it is already done so. So we don't really even need this, and we can safely use our existing variable to read demodulated signal values from this constellation. So here, what we are going to do. Here we are finding which columns have minimum indexes. Yes. Well, basically we find difference, the distance from each column, and here we find these indexes in which columns contain for each symbol minimum distance, and that index is actually the number of the constellation points. So if we look at this diagram, what we are finding are those numbers, green color in brackets. So this index or this index or this index, and accordingly it matches some coordinates. For example, this 11 matches 1 plus 3i. This red matches -1 plus 1i, right? And these are stored in this particular order, meaning that this number will be in the second position, this number will be in the 11th position. At the same time, simultaneously, we can specify the binary code words, for example, in gray mapping, and this way convert these signals into binary code. We are going to return to it very soon, but for right now, let us finish this error calculation. So here we have found the received signal, which, if everything is done correctly, should be exactly the same as this loss signal received, right? So let us calculate the number of errors. So the number of errors is calculated by comparing our received signal and demodulated signal with original signal. Yes, so we are going to use the same notation here. Actually, let me write it myself here. We need some command here too. So prepare matrices, we have done it. Here we find the minimum distance for each symbol, detect symbols. So here we are doing this read detected symbols from CAM16 map. And here we are going to count number of errors. Count number of errors. Like this. So number of errors BER for loss signal, because we are going to calculate number of errors also for Rayleigh channel and for Rayleigh channel, is going to be so first of all, we make the comparison. Yes, so we need to compare our demodulated signal with original signal and check any differences. So the original signal was as loss. So if they have any mismatch, yes, this mismatch will produce result of 1, and any symbols that do match will produce a result of 0. So, for example, I'm going to have one vector x as numbers from 1 to 10, and another vector y as numbers from 1 to 5, and then again from 1 to 5, like this. Sorry, the bracket was incorrect. Like this. So here you can see 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if now I use this command x not equal to y, it's going to produce zeros in whichever positions are the same. So this was first 5 positions, right? And ones in whichever positions are different. Yes, so that's exactly what we need. We need to find how many of these positions are different. So in order to do that, to find how many of these positions are in general, we are just going to add all these ones together. So we can only have either 0 or 1. So summing everything together will produce us the number of these 1 symbols, which is 5, right? And this is actually going to be number of errors. Number of errors, and find symbol error rate. Yes, so symbol error rate. Accordingly, in order to find the probability of the symbol error, we need to divide this number of incorrectly received symbols with the number of total symbols. Yes, so now we have done this operation for normal signal, which is not even with noise. Yes, so we should expect to get 0 errors if we did everything correctly. Let's find it out. Yes, so I'm going to minimize these plots because they are going to be redrawn all the time. We have some warnings here happening. Non-integer range used as index. That is because here we divide with 3000 and down is not an integer number, right? Okay, so what we are going to do is now to round it, just to avoid that warning, because it does it anyway. Yes, it automatically rounds it. But to avoid this type of warning, we are going to fix that problem. So also, I don't want to see this string message. I think I missed semicolon here. Yes, I do. So for that reason, it displays in the command line the entire result. So if I run it once again, I have only this BER loss for direct line of sight signal. Error probability is 0, as it should be. If I add noise, it will become worse and worse, but we'll return to noise a little bit later. Right now, let us make the copy of, well, or actually, no, we do need a copy of this. Or wait a minute, how to make it better? We can actually make this a separate file, right? Like this, yes, and then call it with a single line. But well, our program is already too big. Let's see if we will change anything here. We don't change anything here because all that changes is this SRX and this P error loss. So actually, I think it is quite a good idea to make this a new file, because we are going to use this approach in for loop later on, similarly as it was here 3 times. Yes, so here it was okay to use this in the for loop, but if I now copy this 2 more times, it will be too much text. So I'm going to, copy this part and save this as CAM16 demod. Okay, so instead now of all this text, I'm going to call my script CAM16 demod. So this will demodulate data. And if everything is done correctly, then it is the same. So all we need to do now is to make 3 more copies of this case. So we will be generating a new noise each time for each signal, because they have different average power, and accordingly different strength of noise is needed to achieve the specific signal to noise ratio. So we'll get to noise calculations later, but for right now, noise is going to be the same for all of these signals. So let us make it like this: the modulated data, and then count number of errors. Accordingly, also will be commented like this. And now we can do it like this. So the modulated line of sight signal, no fading. We are going to copy it. Here we are going to use RX Rayleigh channel. So the modulate Rayleigh channel with fading, right? And similarly, here we are going to do so for the Rayleigh channel. Rayleigh channel. Also, we want to save this as a specific Rayleigh channel number of errors. Similarly, here we are going to have Rayleigh as, and here also Rayleigh. So now we are going to have three numbers of errors: one for loss of direct line of sight signal, one for the Rayleigh channel signal, and one for the Rayleigh channel signal. So let's see how it looks like. And you can clearly see these numbers are different. Actually, the error probability of the Rayleigh channel is very high. The worst possible value we could expect here was 0.5. Yes, and well, we are quite close. Yes, 0.5 means that it's completely impossible to tell whether we will receive correctly or not. That is complete chaos. Yes, for Rayleigh channel, the situation is not so bad, but this is only because we have value equal to 5 of k. Yes, if I set value of 2, actually let us also increase number of simulation symbols. Yes, I believe 5 is not going to be large. Our goal is to have 6 here. Yes, so 1 million symbols. But in order to debug and test our program, currently we are not going to set 6 here because otherwise it may make us wait long time. And the error probability changed and became worse. Yes, because I have reduced k. Actually, if I set k to 1, we should see the same results for Rayleigh and Rayleigh channel. Well, basically, actually for Rayleigh channel with k1, it's even worse than for Rayleigh channel. Yes. Okay, wait a minute. Ah, I missed. It looked like this plot was like too condensed for some reason. I don't know why. Well, actually, let us make this command close all, because I believe somewhere here these points add up. Well, let us maybe try and run a few more times our code. Yes, it does look like they are drawn on top of the existing points. Yes, and there we can see more and more of these points. That's, of course, because we have this hold on and hold off. Yes, for that reason, we need to close all the windows each time we run the simulation. So if you happen to forget to do so manually, you can specify a command that will instead close all windows automatically. Yes, so now these windows will be redrawn each time. Yes. If I run it again, they are closed and then drawn again. Well, because noise was really disproportional, in this particular case, you can see that the limits for x and y axis are different. Well, that is a random thing to happen. Sometimes it happens, sometimes it's not. Yes, now we have 10 in both cases here, 6 in both cases here. Okay, so, and we have 3 error probability values. Yes, so you will need to include in your report for k equal 2 and k equal 5. I'm going to return k equal 5 because it obviously will produce the good difference between Rayleigh and Rayleigh channel, but k equal 2 is also somewhat different, right? Just not that much. Okay, so now we have simple error rate probabilities, and what we need next is binary error probability. And I can already see that we are close to 1 hour already, so this is quite good moment to make a short break of, let us say, 14 minutes, right? And then after the break, we will conclude this practical exercise, which is going to take us another probably 45 minutes to finish. So are there any questions so far? Is everything working? Do you have any problems with previous exercises? Maybe. So if you run into any problems, as always, you can contact me at any time. I will be glad to help you. So let us have then this break and see you in 14 minutes at 9 or 10. Yes. Thank you, and we'll be back soon.